Hi, welcome to this lesson. In today's lesson, we'll be talking about Graham's law and ideal gases. This is the fourth and final part of this series. We talked about so many other aspects of gas laws in part 1, part 2, and part 3. So, if you need to catch up, you can go back and watch those other videos. You can browse the channel and watch those other videos. You can also share this channel with your friend. Those who might find this content very handy, and they are very, very important. There are a lot of IGCSE concepts being discussed, a lot of Y concepts being discussed, and then other very important exams. So you find it very handy. So I recommend that you recommend this channel to your friend and subscribe, so that when we upload new and informative content, you will be kept in the loop. So before we go further, we will be discussing molar volume and molecules. What is the relationship between molar volume and molecules? So one of the things you must know is that 1 mole of any gas contains 6.02 times 10 raised to power 23 molecules. Any gas at all, 1 mole of it contains 6.02 times 10 raised to power 23 molecules. This is known as the Avogadro's number. And then at standard conditions, which is standard temperature and pressure for gases, 1 mole of any gas also contains 22.4 dm cube. So if you are familiar with the metric system, you can convert 22.4 dm cube to cm cube and see what it will give you. I think you should get 22,400 cm cube. So we can also say that 1 mole of any gas occupies a volume of 22.4 22,400 cm cube. And then we also said in the previous videos that dm cube and liter are approximately equal. So we can also say 1 mole of any gas at standard temperature and pressure contains 22.4 liters. So let's just see some illustrations. Okay, 1 mole of hydrogen gas, based on what we've said so far, contains 22.4 dm cube of hydrogen gas, as that will be the volume at standard temperature and pressure. When the temperature and pressure is not standard, it may not be 20.4 dm cube, but when it is standard temperature, when it is standard pressure, the volume of the gas should be 22.4 dm cube. And then standard temperature, based on our previous discussion, is 273 Kelvin, that's standard temperature. And then standard pressure is 760 millimeter mercury, or 1.013 times 10 to the power 5 Newton per meter square. So you can go back to the previous video to get acquainted with this concept. And then 1 mole of carbon 4 oxide gas as well will contain 22.4 dm cube. And then the number of molecules it will have as well will be 6.02 times 10 to the power 23. And then 1 mole of carbon 4 oxide, the molar mass of carbon 4 oxide is 44 gram. So we can also say 44 gram of carbon 4 oxide contains 6.02 times 10 to the power 23 molecules, or would occupy a volume of 22.4 dm cube. So take note, it's very, very important. The same applies for hydrogen. 1 mole of hydrogen has a molar mass of 2 grams. And then we could say that 2 grams of hydrogen has 6.02 times 10 to the power 23 molecules and occupies a volume of 22.4 liters, or dm cube as the case may be. Okay, so let's look at these questions together. Question 1 says, how many molecules are in a molar volume of a gas at standard temperature and pressure. So based on our previous discussion, at standard temperature and pressure, one mole of any gas will occupy a volume of 22.4 dm cube and would have 6.02 times 10 raised to the power 23 molecules. Very, very important. Okay, the other part of the question says how many molecules are in a molar volume of a gas at 20 degrees Celsius. At 20 degrees Celsius and standard pressure, it will still be 6.02 times 10 raised to the power 23 molecules. Take note. So as long as the pressure is standard, irrespective of the temperature, the number of molecules will be the same as long as it is 1 mole. Okay, let's move on. So in the second question, we are told to, in an experiment, 112 cm cube of carbon dioxide gas were collected at STP. How many molecules of the gas are present? So Avogadro's constant was given, and then molar volume at STP was also given. So 112 cm cube of carbon dioxide were collected. How many molecules of the gas are present? So in this calculation, I converted 112 cm cube to dm cube. It's not necessary anyway, but it can also be done. So since 1000 cm cube makes 1 dm cube, so when you divide 112 cm cube by 1000, you get 0.112 dm cube. So we said that 1 mole occupies a volume of 22.4 dm cube. So that means if you want to know the number of moles in 0.12 dm cube, you just divide 0.112 by 22.4 and then you get 0.005 moles. So that's the number of moles. So, and then it says find the number of molecules. You know that 1 mole has 6.02 times 10 to the power 23 molecules. So if there are 0.005 mole, you just multiply it by 6.02 times 10 to the power 23, and then you get 3.01 times 10 to the power 21 molecules for 112 cm cube. An alternative to doing this would be to divide 112 by 22,400 to get the number of moles, because 1 mole also occupies 22,400 cm cube. So you need to convert to dm cube, and then it will still give you 0.005 moles, and then the other calculations will be done as usual. So I hope you understand. If you are finding anything difficult, endeavor to let me know in the comment section. Okay, before we move on to Graham's law, it is very, very important we also understand what vapor density is, and then how are they related, how is it related to relative molecular mass. Vapor density is a ratio of gas volumes. It has no unit, right? It's a ratio of the mass of a gas to the mass of equal volume of hydrogen gas. So a ratio of a particular volume to a ratio of equal volume of hydrogen gas. Why hydrogen gas? Hydrogen gas is the lightest gas known. So once we compare the volume of every gas with hydrogen, it could stand as the basic standard. So basically what we are saying is vapor density Vd is equal to mass of given volume of gas over mass of equal volume of hydrogen. So since equal volume of a gas contains the same number of molecules, we could say that vapor density is also equal to mass of n molecules of gas over mass of n molecules of hydrogen. And then if n cancels out, as you can see on your screen, we can say that mass of one molecule of gas over mass of one molecule of hydrogen will also give you the vapor density. So mass of one molecule of a gas is the relative molecular mass. So we can also, and the mass of one molecule of hydrogen is 2. So we can say vapor density is relative molecular mass of any gas divided by 2. Another way of saying it is relative molecular mass is equal to 2 times vapor density. Very, very important. Okay, hope you understand. If you do not, if you are confused at any point, you know what to do. And once you comment in the comment section, I would reply as soon as possible. Okay, let's look at these questions. What is the vapor density of sulfur 4 oxide? And then question 2 is, if 400 cm³ of a certain gas weighs 0.5 gram at STP, calculate its molar mass and vapor density. So sulfur 4 oxide, what is the vapor density? So first, because we say vapor density is relative molecular mass divided by 2, it means that we need to calculate the relative molecular mass or the molar mass of sulfur 4 oxide. Sulfur is 32 from what we have here, and then oxygen is 16, and so 32 plus 2 times 16, because in the formula there are 2 molecules of oxygen. So 32 plus 2 times 16 will give us 64. And then applying the formula, vapor density is relative molecular mass over 2. It is something as saying 64 divided by 2, which is 32. So whenever you are given any gas, just calculate the relative molecular mass of that gas and divide by 2. You will get its vapor density. Okay, in question 2, you say if 400 cm³ of a certain gas weighs 0.5 gram at STP, calculate its molar mass and vapor density. So what we are saying is 0.5 gram of the gas is 400 cm³. Then how do we get the mass of 1 mole? So molar mass would have a volume of 22,400 cm³. So once we compare those two numbers, 0.5 grams occupies 400 cm³. Molar mass from our previous discussion should occupy 22,400 cm³. So once you take ratios and divide, you get that molar mass is 28 gram per mole. So you can use these relationships to calculate vapor densities as well. We dealt extensively with this kind of relationships and statement of equivalence in the previous videos. So when you go back, you understand why these calculations are like this better. So and then the second part of the question says we should calculate the the vapor density of the gas. So since vapor density is relative molecular mass divided by 2, it means that vapor density for this gas is 28 divided by 2, which is 14, as you can see. Okay, let's move on. Okay, do this activity, and then to just test yourself. What's the point of watching this kind of video without testing yourself to see if you are following? So this link will also be in the description, so that it will be easy for you to click and then and do the activity. Okay, let's quickly talk about ideal gas equation. So for a fixed amount of a gas at constant pressure, from Boyle's law, volume is inversely proportional to pressure. And then from Charles' law, volume is directly proportional to temperature. These are things we've covered in previous editions of this lesson. So endeavor to to watch, and then if you are confused. Volume is inversely proportional to pressure. It's a statement by Robert Boyle. And then volume is directly proportional to temperature. It's a statement by a statement of Charles' law. And then volume of a gas is also directly proportional to number of moles. Certainly, the higher the number of moles, the higher the volume, and the lower the number of moles, the lower the volume. They are in direct proportion. So when we combine these three statements, what are we going to have? We have a joint relationship. Volume is directly proportional to number of moles and temperature, and inversely proportional to the pressure, as you can see. So once we introduce the constants, a constant, we have that volume V is equal to R NT over P. And then once we rearrange properly, we'll have that by cross multiplying, PV is equal to nRT. This is called the ideal gas equation. It's very, very important in chemistry. The ideal gas equation: P is pressure, V is volume, N is the number of moles, R is what we call the molar gas constant, and then T is temperature. Okay, so the value of R is given by 8.31 joules per mole per Kelvin. So this one value, and then another value depending on the unit that is used for P, V, N, and T. N, the unit of N is usually the mole, and then T, the unit is usually the Kelvin. So depending on the unit used for pressure and volume, it can also be 0.0821 liter atmosphere per mole per Kelvin. You know that 1 liter is same thing as 1 dm cube, so it could also be 0.0821 dm cube atmosphere, that's atm, per mole per Kelvin. So but how did we arrive at this? So if we make R the subject of the formula, we have that R is equal to PV over NT. Here, all we have here, R is equal to PV over NT. So under standard condition, P is equal to 1.013 times 10 raised to the power 5. That's standard pressure. And then when the number of moles of the gas is 1, the volume of that gas is 0.0224 meter cube. If you are using SI unit, it will be dm cube between 2.4 dm cube. But if you convert dm cube to meter cube, it will be 0.0224 meter cube. From our metric system, we know that 1000 dm cube make 1 meter cube. So if you divide 22.4 by 1000, you get this value right here. So that's the standard that's the molar volume for 1 mole of a gas. So and then standard temperature is 273 Kelvin. So once you multiply and divide, you get 8.31 joules per mole per Kelvin. Somebody looking at it may be saying, where is the joules coming from? Yes, using dimension analysis that we do in science. Once you multiply m raised to the power minus 2 by m raised to the power plus 3, you will get m. So that means it will be Newton meter as at the numerator, and then mole and Kelvin at the denominator for the unit analysis. So Newton meter is joules. So that's where the joules is coming from. So if you have further questions, endeavor to let me know. If another different set of units are used, ideal gas constant or universal constant will also be different. For example, if we choose to use 1 atmosphere as standard pressure, and then 22.4 dm cube or liter as the volume of 1 mole of a gas, and then once we multiply and divide, we'll get that the value of R is 0.0821 liter atmosphere per mole per Kelvin. So it depends on what you are given. If you are given pressure in liter in Newton per meter square, and then we are given, yes, in Newton per meter square, and then the volume of the gas in meter cube. You know that this is the gas constant to use, 8.31 times 10 so joules per mole per Kelvin. But if you are given pressure in atmospheres, and then volume in dm cube, then you know that R is equal to 0.0821 liters atm per mole per Kelvin is the gas constant to use. So however, you can also interconvert, so because sometimes pressure may be given in Newton per meter square and volume may be given in dm cube. So you need to convert appropriately before you can use the respective gas constant. Okay, yes, we're talking about ideal gases. I think it's very important to discuss what are ideal gases, and then what are real gases. First and foremost, ideal gases do not exist. Ideal gas is a theory proposed to explain the behavior of a gas under standard conditions, and then certain assumptions were made that if the gas is to behave like this under standard conditions, it means that intermolecular forces between the gas molecules should not exist. And then yes, intermolecular forces should not exist, and then volume of the molecules should be negligible, and then collisions between gas molecules should be perfectly elastic. But in the real sense, gas molecules has a volume, and so however that volume is small, it does exist nonetheless. So it is very important to understand that ideal gases exist in theory only. The gases that we deal with are real gases, and then they exhibit certain variation from ideal behavior under certain conditions. So that's very, very important. So real gases are the gases that we are conversant with. Ideal gases is what a gas should behave like under standard conditions. So the first theory for gases is, number one here is molecules move in continuous random straight line motion. Yes, that's an ideal gas. It's expected that the molecule should move continuously. In real gases, still obey this principle, and then but sometimes the motion can be influenced by intermolecular forces, as you can see here. So however, on a general scale, we can assume that real gases still follow this behavior. Okay, another number two says volume of gas molecules is negligible. That's for an ideal gas. That's the assumption for an ideal gas. For real gases, we say that molecules of gas actually occupy a volume. It might be small compared to the volume of the container, but it does exist nonetheless. It is negligible when the pressure is low. The pressure is low. That means at high pressure, molecules of a gas, the volume becomes significant compared to the container. But at low pressure, it is largely true. So this property is true at low pressure, but it becomes untrue at very high pressure. Okay, number three is no intermolecular forces exist in gases. No, there are intermolecular forces in gases, majorly the van der Waals forces, because they are assumed to be molecules. Okay, so however, these intermolecular forces are negligible, are very, very small. They exist anyway. Um, at low temperature or high pressure, attractive forces can become very significant. As a matter of fact, they can cause the gas to condense. That is why cooking gas in a gas cylinder appear to be liquid, because it has been compressed at very high temperature and usually lower temperature than the temperature of the atmosphere. So there are intermolecular forces, but these forces become very prominent at low temperature and high pressure. So collisions are perfectly elastic, is what number 4 is saying. Um, collision may be sometimes perfect, maybe slightly inelastic. We are talking about real gases. Energy can be lost and all that. So it's not perfectly elastic as such, but at low pressure and then high temperature, um, this the ideal behavior of a gas becomes more prominent. Real gases tend to behave like ideal gases. Okay, this is another task. Endeavor to do them. You are required to study the notes in the link and then answer the question. I'm telling you, these questions will help you understand what we've been talking about all the while. And then if you are confused at any point, you could let me know in the comment section and I will respond as soon as I can. There's no need watching this kind of video and not testing your understanding. So please do the needful. The link to this note will also be in the comment, in the description of this video, so that you could study them and then answer the questions as well. It's very, very important. Okay, finally let's go to Graham's law of diffusion. Graham's law of diffusion states that the rate of diffusion of a gas is inversely proportional to the square root of its molar mass or density. So don't forget, rate of diffusion of a gas is inversely proportional to the square root of its molar mass, or you can also say it's inversely proportional to the square root of its vapor density. So in symbols, mathematically, this is how it's represented. R is for rate of diffusion, and then inversely proportional to root of the molar mass. And then also if we take the density approach, R is inversely proportional to the square root of its vapor density. So if we rewrite it properly, and then it means that for the first one, R1 over R2 is equal to square root of M2 over M1. Take note, when R1 is up, M1 is the denominator, and then if R2 is the denominator, M2 is the numerator. So it's an inverse relationship. And then also, if we take the density as well, R1 over R2 is equal to square root of D2 over D1. Very important, take note. So also, the rate of diffusion of a gas is inversely proportional to the time it takes. So what we mean is, if the rate of diffusion of a gas is high, it will take less time for the gas to diffuse. And then if the rate of diffusion is low, it will take more time for the gas to diffuse. It's an inverse relationship as well with respect to time. So that means Graham's law can be expressed in any of these ways. R1 over R2 is equal to T2 over T1. It can also be R1 over R2 is equal to root M2 over M1. R1 over R2 is equal to root D2 over D1. Time can also be used at any point if you don't want to calculate the rate. You can take any of this equation, any aspect of this equation, and equate it to each other. You can say T2 over T1 is equal to root M2 over M1. and so on and so forth. So depending on how the question comes. So but this can be extrapolated from Graham's law of diffusion. Okay, let's check out this question. Compare the rate of diffusion of hydrogen gas and oxygen under the same condition. Molar mass of hydrogen is 2 gram per mole. Molar mass of oxygen is 32 gram per mole. So that's question 1. And question 2 says the starting gas 1.5 times faster than nitrogen gas. What is the molar mass of the unknown gas? So let's see. So first you must understand that R1 over R2 is equal to M root M2 over M1. Why are we using M molar mass, not vapor density? Because the molar mass of the gases is what is provided in the question. So you only use what you can get from the question, or what you can deduce from the question, either directly or indirectly. So for hydrogen, if we take hydrogen as the first gas, we can say the rate of diffusion of hydrogen gas over the rate of diffusion of oxygen gas is equal to the molar mass of oxygen over the molar mass of hydrogen. So don't forget to invert it when you are substituting, because it's an inverse relationship. So at the end of the day, once you divide and take square root, you will get that it is 4. It means that hydrogen diffuses 4 times than more than oxygen, 4 times faster than oxygen. Okay, let's go to the second question. You say a certain gas diffuses 1.5 times faster than nitrogen gas. So it means the rate of diffusion of the unknown gas divided by the rate of diffusion of nitrogen gas is equal to 1.5. That's what the statement basically means. So if we use Graham's law of diffusion, it means rate of the unknown gas over rate of nitrogen gas is equal to molar mass of nitrogen over molar mass of the unknown gas. So once we substitute, we would have the rate of the unknown gas over rate of nitrogen is 1.5 from the question. Molar mass of nitrogen is 28 gram per mole, and then we are to calculate the molar mass of the unknown gas. So once we square both sides, we would have that 1.5 square is 2.25. So you see, then we would have, that means the square root sign will go in the other side of the equation. So it means that when we solve properly by cross multiplying, we'll have that molar mass of the unknown gas is 28 over 2.25, which is 12.44 gram per mole. So take notes, study them carefully. Let me know if I need to explain further. Okay, this is another task based on what we've done so far. So the link will be in the description as well. Do these activities. They help to test your understanding. They help to strengthen your understanding of what we are doing here. And then the Google Forms can be done over and over again. So and then the answers, you can review the answers each time. It's very, very important. Okay, let's talk about mass, mole, and gas volume relationships. So it's very, very important. We've done similar things in previous videos. So I would advise you review, and then for better understanding. Okay, in this equation, sulfur 4 oxide reacts with oxygen to form sulfur 6 oxide. As you can see from the state symbols, all of them are gases. Reactants are gases, and then products are gases. So, and then I've also included the molar mass, or rather, yes, molar mass and reacting mass in the equation. For example, the molar mass of sulfur 4 oxide is 64, and then there are 2 of them, so the reacting mass is 2 times 64. the molar mass of oxygen is 32, and then that's the reacting mass in this case. The molar mass of sulfur 6 oxide is 80, and there are two of them, so it is 2 times 80. So what equivalent statement can we get from this? First, we can say 2 mole of sulfur 4 oxide is equivalent to 1 mole of oxygen. That it means that 2 mole from the equation of the reaction, 2 mole of sulfur 4 oxide requires 1 mole of oxygen in order to form 2 moles of sulfur 6 oxide. So we can build an equivalent statement that 2 mole of sulfur 4 oxide is equivalent to 1 mole of oxygen. And then, since the reacting mass of sulfur 4 oxide is 128 gram, we can say 128 gram of sulfur 4 oxide is equivalent to 32 grams of oxygen. So remember, the reacting mass of sulfur 4 oxide is 2 times 64, so which is 128. So 128 gram of sulfur 4 oxide is needed to react with 32 gram of oxygen. Remember, we also say that 1 mole of any gas occupies a volume of 22.4 liter or 22.4 dm cube. So, but there are two moles of sulfur 4 oxide. That means when you multiply it by 2, you get 44.8 liters. That's the reacting volume. 44.8 liters of sulfur 4 oxide is equivalent to 22.4 liters of oxygen. That's 22.4 dm cube of oxygen. Very important. So these are equivalent statements. More equivalent statements can be deduced from this reaction. And then we can also say 128 gram of sulfur 4 oxide is equivalent to 22.4 liters of oxygen. So 128 grams of oxide equivalent to 22.4 liters of oxygen. So it means that 128 grams of sulfur oxide is required to react with 22.4 liters of oxygen. These are varying different statements. And we can also say that 128 grams of sulfur 4 oxide is equivalent to 44.8 liters of sulfur 6 oxide. So because sulfur 6 oxide is 2, and then each of them is 22.4 dm cube. So that means 2 of them is 22.44.8 liters or dm cube. So the 2 grams of oxygen is equivalent to 44.8 liters of sulfur 6 oxide. So these are equivalent statements. So go through this equivalent statement, the final equivalent statement, and see for yourself if you are following. 2 moles of sulfur 4 oxide is equal to 44.8 liters of sulfur 6 oxide, for example, and all the others. So I'll give you a few seconds before I move on. You can also pause the video to make better sense of what we've talked about so far. Okay, I presume you are done now. If you have any concerns, you know what to do. Okay, so for this reaction, where hydrogen gas reacts with chlorine gas to give you hydrogen chloride gas. So the reacting mass of hydrogen is 2. There's the molar mass of hydrogen is 2. The molar mass of chlorine is actually 35.5. The relative atomic mass of chlorine is 35.5. But we're talking about a molecule of chlorine. So the relative molecular mass of chlorine is 71. And then hydrogen chloride, the reacting mass is 2 times 36.5. Each mole is 36.5, and then because there are 2 of them, multiply by 2. So you can get more equivalent statements. So I'll leave you to study them, and then you can even write other equivalent statements that I didn't capture in this section. It helps you to understand this concept better because we'll be using them as we move on. So these are equivalent statements that we can derive from this equation. I hope they are the same with what you wrote, or if you have already watched the video to this point, you can write the ones that are not included in this video. So you can write, there are so many equivalent statements that can be written from just this single equation. So it helps you to establish relationship between reactant and product, and then you can easily take ratios and calculate as required, as may be required. So I'm going on now. If you have any concerns, please do let me know. Okay, let's look at this question together. Look, there's an equation: carbon plus oxygen will give you carbon dioxide, right? How many volumes of pure carbon will burn in 2.8 dm cube of oxygen completely at STP? What will be the volume of carbon dioxide produced under the same conditions? So you will see now that equivalent statements will come in handy in solving questions like this. So how many volume of pure carbon will burn in 2.8 dm cube? So we are giving, from the equation, we have 1 mole of carbon reacting, and then we are giving, in the question we are giving 2.8 dm cube, which is volume of carbon. So you can write the relationship between mole of carbon and volume of oxygen, because you are told to calculate volume. So if the relationship between mole and volume, if volume is involved in your relationship, you can calculate any other volume that is required. So that's why the relationship we are taking out is 1 mole of carbon is equivalent to 22.4 dm cube of oxygen, since there's only 1 mole of oxygen in the equation. Okay, and then x mole of carbon will be equivalent to 22.8 dm cube according to the question. We do not know. Let x stand for the number of moles that will give us 2.8 dm cube. So once we take ratios, x divided by 1 is equal to 2.8 divided by 22.4. We would have that, and solve, we'll have that x is equal to, we'll have that x is equal to 0.125 mole of carbon will be required. Okay, I see there's a mistake in the typing of the question I just discovered. I will not be editing, so please take note. It's saying how many volumes of pure carbon. The question is supposed to be how many moles, please, of pure carbon. So take note, sorry for that mix-up. How many moles of pure carbon? So very important. Okay, let's go to the second part of the question. What will be the volume of carbon dioxide produced under the same condition? So we're talking about volume of carbon dioxide. So we are saying the relationship should contain volume, moles and volume, importantly. So 1 dm cube of oxygen is equivalent to 1 dm cube of carbon dioxide, and then 2.8 dm cube of oxygen is equivalent to 1 dm cube of carbon dioxide. How do we get this statement? Since we're talking about volume, the relationship can be in any way you want it. You can write a relationship between the number of moles of carbon and then and volume of carbon dioxide. For example, you can say 1 mole of carbon is equivalent to 22.4 dm cube of carbon dioxide. That means 0.125 and so on will be equivalent to what? So what will be the volume of carbon dioxide? So here from the equation we can see that one volume of oxygen is equivalent to 1 volume of carbon dioxide. So 1 dm cube of oxygen is equivalent to 1 dm cube of carbon dioxide. And then if oxygen is 2.8 dm cube, then it's equivalent to y dm cube of carbon dioxide. So once you solve by taking ratios, y over 1 for carbon dioxide is equal to 1 over 2.8 for oxygen. You would have that the volume of carbon dioxide that will be produced in this equation will be 2.8 dm cube as well. So study the calculations very well, and I think you understand better. So any relationship can be drawn. You can draw a relationship between moles and volume, and then mass and volume, as long as it will help you in calculating or answering the question. You can even draw a relationship between volume and volume, mole and mole, mass and mass, etc. So as long as it will help you to solve the problem given. Okay, calculate the amount of hydrogen sulfide required to react completely with 4 dm cube of sulfur 4 oxide at STP. Okay, the equation for the reaction has been given. It's on your screen. And then 1 mole of a gas occupies 22.4 dm cube at standard temperature and pressure. So from the equation of the reaction, now remember, we are calculating the number of moles of hydrogen sulfide that will react with 4 dm cube of sulfur 4 oxide. So number of moles, volume relationship is what we are doing, because that's what we are looking for. And then you are giving volume. So both of them should be in your relationship so that you can easily take ratios. It's very, very important. So, and then from the equation of the reaction, we have that 2 moles of HCl, of H2S, is 22.4 dm cube of sulfur 4 oxide. So how many moles will be equivalent to 4 dm cube as required in the question? So when you take ratios, x over 2 is equal to 4 over 22.4. So ratios from what we have. And then at the end of the day, once you solve for x, you have that x is 0.357 mole of hydrogen sulfide gas. So very, very important. These are ratios, and writing equivalent statement would help you in this sort of calculations. So remember, the question required the number of moles. It gave you volume. So it's expedient to write a relationship between number of moles and volume. Okay, magnesium of mass 1.2 grams react completely with chlorine. Write a balanced equation for the reaction. Calculate the volume of chlorine used at STP. So magnesium is Mg, react with chlorine. Chlorine is Cl2, that's the chlorine gas. So Mg plus Cl2 will give you MgCl2, right? So as you can see on your screen. So this is a balanced equation. Check both sides. The number of magnesium on the left is 1. The number of magnesium on the right is 1. The number of chlorine on the left, the chlorine atoms now is 2. Number of chlorine atoms on the right is equal to 2. So take note. So we've answered the A part of the question. Let's go to the B part. The B part says calculate the volume of chlorine used at STP. So we are given mass of magnesium, and then we are asked to calculate volume of chlorine. So the relationship you should write should be that of mass of magnesium and volume of chlorine, so that you can easily take ratios and solve. Don't write relationship outside what you need and outside what is required. It's very important. Some students fall victim to this, and then at the end of the day, they are not able to solve the problem. So your relationship should be what you were given, or what you can easily deduce, and what you are looking for. So from the equation, the molar mass of magnesium is 24. It means that 24 grams of magnesium is equivalent to 22.4 dm cube of chlorine. And then so from 1.2 grams of magnesium will be equivalent to x dm cube of chlorine as required. So once you take ratios, so x divided by 22.4 is equal to 1.2 divided by 24. So ratios from the same sides. So once you cross multiply and solve, you will have that x is equal to 1.12 dm cube of chlorine. Very simple. Once you write statement of equivalence, a lot of things are simplified in chemistry. Okay. Okay. So let's continue. Example 8. Okay. Example 8 is calculate the volume of potassium hydrogen thiazocarbonate 4 calculate the volume of potassium hydrogen thiazocarbonate 4 oxide produced at STP when 1 kg of potassium hydrogen thiazocarbonate 4 is totally decomposed. Okay, I apologize for that. Calculate the volume of carbon 4 oxide, please. Carbon 4 oxide, take notes. The volume of carbon 4 oxide produced at STP when 1 kilogram of potassium hydrogen thiazocarbonate 4 is totally decomposed. Okay, this is the equation for the reaction. This is potassium hydrogen thiazocarbonate 4, and then this produces carbon 4 oxide at the end of the day. So we are calculating the volume of carbon 4 oxide, volume, and then we're giving mass of potassium hydrogen thiazocarbonate 4. So the relationship should be between mass of potassium hydrogen thiazocarbonate 4 and volume of carbon 4 oxide. So from the equation, the molar mass of potassium hydrogen thiazocarbonate 4 is 100, but the reacting mass is 200 because there are 2 moles reacting. That's why we have 200 grams. Just multiply by 2. And then since there is 1 mole of carbon 4 oxide, and then the molar volume of a gas is 22.4 dm cube, it means 200 grams of potassium hydrogen thiazocarbonate 4 occupies a volume of 22.4 dm cube of carbon 4 oxide. And then we're giving 1 kg in the question. 1 kg is 1000 grams. So 1000 grams of potassium hydrogen thiazocarbonate 4 will be equivalent to X, or any alphabet for that matter. So once we take ratios and then solve, you get that the volume of carbon 4 oxide is 112 dm cube. So I hope these things are clear enough, and you can practice them on your own to gain mastery, and then make sure you do the exercises that will help you to understand better. Okay, I've included how to calculate potassium, the molar mass of potassium hydrogen thiazocarbonate 4 for anybody who might be having challenges calculating it. Potassium is 39, hydrogen is 1, carbon is 12. Okay, example 9. Bleaching powder manufacturing dictates HCl according to the following equation. So this is the equation for the reaction of bleaching powder with hydrogen chloride. Calculate the mass of bleaching powder that will produce 400 cm cube of chlorine at 25 degrees Celsius and a pressure of 1.2 times 10 raised to the power 5 Newton per meter square. So the standard conditions and other things were provided. Okay, this is the balance equation for the reaction is also has been rewritten so that you understand better. So this is the calculations involved. But before I go into explaining the calculations, I'd like to explain this other one. Now, this relationship, 143 grams of bleaching powder is equivalent to 22.4 dm cube of chlorine, is an equivalent statement from the equation. The molar mass of bleaching powder was calculated and is 143 grams. So it's equivalent, and then the number of moles of chlorine is 1. So and the volume is 22.4. So we can say 143 gram of bleaching powder, 22.4 dm cube. Now, but this is true when the reaction occurs at standard temperature and pressure. So the 1 mole of any gas would occupy a volume of 22.4 dm cube at standard temperature and at standard pressure. This reaction, where the bleaching powder reacts with hydrogen chloride, the reaction is not at STP, it occurs at 25 degrees Celsius. And then it at a pressure of 1.2 times 10 raised to the power 5 Newton per meter square. So you need to find, that is when the volume of chlorine is 400 cm cube, as you can see. So you need to find the volume of chlorine at STP. That is when this statement becomes relevant, because 1 mole of chlorine gas from the equation would only occupy 22.4 dm cube at STP. So if the reaction is not occurring at STP, you need to convert the volume provided to the equivalent volume at STP, so that you can use this statement of equivalence. So that's what we are using. That's what we are doing here. So using the general gas equation, if you have issues with the general gas equation, probably you do not understand what it means, it has been dealt with in the previous videos, please go back and watch so that you can have a better understanding. So P1 V1 over T1 is equal to P2 V2 over T2 is equal to P3 V3 over T3, and so on and so forth. But you can see in this equation, I am using P0 V0 over T0. It is because the volume we want to calculate is at STP, and then the initial conditions were the first conditions given. So we are going back to standard condition. So we are not moving from standard condition to a particular condition. We are moving from a particular condition to standard condition. But it doesn't matter. You can still use your P1 V1 over T1 is equal to P2 V2 over T2 if you assume that the second set of conditions are for the standard conditions. So once we make the volume at standard conditions, which happen to be V0, as the subject of the formula, this is what we would have. And then we substitute. P1 is the first pressure given in the question, V1 is the volume 400 given in the question, and then T1 is T0 now, right? Is the volume, is the temperature at STP, which is 273. P0 is the pressure at, or P0 is the pressure at STP, which is in this case we're using 1.01 times 10 to the power 5 Newton per meter square. And then T1 is the first temperature, that's 25 degrees Celsius. If you observe, we have to convert 25 to Kelvin, 25 degrees Celsius to Kelvin, because the temperature we use for gas laws are absolute temperature, which is gotten by adding 273 to the Celsius temperature. Also, this was covered in the previous videos, so endeavor to catch up if you have to. So once we substitute and divide, we'll get that at STP the volume is 0.4354 dm cube. If you observe, I converted the volume here 400 cm cube to dm cube by dividing by 1000. That's how I arrive at 0.400 dm cube. You can use it that way, but at the end of the day the answer will be in cm cube, not in dm cube. So and if you are using dm cube here, this one also must be dm cube. So, but if you choose to use cm cube, it means that this one also will be in cm cube. It will be 22,400 cm cube. So whichever unit you want to use, the idea is for there to be balance, for there to be equivalent on both sides. Okay, so from what I've said before, we said that 143 gram of bleaching powder, it gives you 22.4 dm cube from the question. And then what mass of the bleaching powder will give you 0.4354 dm cube. So from here now it's easy because you've written an equivalent statement. All you need to do is to say x over 143 is equal to 0.4354 over 22.4. So and then cross multiply and divide. You get that the mass of the bleaching powder will be 2.779 gram. So everybody learns at different paces. So don't be disappointed when you don't understand at first try. That is why it's a video, a recorded video. You can watch over and over again and try to solve these questions on your own without the video. That's one way to learn things like this. So some persons are very smart and very fast. By just watching the video, they understand what's going on already. Good for them. And some persons learn at a slower pace. So we are not all the same. So we don't expect us to learn at the same rate. So if it appears to be hazy and difficult, take your time. Watch repeatedly. Write out the questions. Try to solve them on your own. Take charge of your learning. That's one way to learn very well in chemistry. So this is another task. So do the task. If you have any difficulty, let me know in the comments section. Sorry, I'm moving my camera around. Okay, so I would have to move this around so that you can see what we are talking about. Okay, yeah. And so these are the questions. If I were you, I'll write them down and see if I can solve them. If you have difficulty, you can always let me know in the comment section. Okay, thank you. We've come to the end of this presentation. Please subscribe to our channel and then share with your friends. It's very, very important.